Hi, welcome once again to Math as a Second Language, where today we continue our prelude to fractions, meaning we want to show again why the concept of prime numbers, multiples, etc., is so important to understand prior to studying fractions. In other words, if we can get this in such a way that students see this clearly in their mind, using the adjective-noun theme, they'll never again have to think about fractions any differently than they do think about whole numbers, okay? Now, we saw last time that whenever you multiply two numbers together, the product is a common factor of both. For example, with 8 times 15, it's the 8th number you come to if you're counting by 15s, and the 15th number you come to if you're counting by 8s, okay? But sometimes that's not the smallest number that works. Now, especially prior to the age of calculators being so common, the idea was, all you really need is a common multiple. You don't need the least common multiple. But the idea was, since there were no calculators, the smaller the common multiple, the less chance there would be for a mistake to be made mathematically. So out of respect for that, we still stress the least common multiple, least common denominator, stuff like this, even though the important thing is to say, find a common denominator, find a common multiple. So let's go on from there, and let me show you where the problem comes in. I love to use the quotation that it's easier to scramble an egg than to unscramble one. That's the elementary school students' version of what in advanced physics we call the law of entropy, that things take place in the direction of least resistance. Well, what I mean by that here is, if I say to you, how much is 37 times 43, either by longhand or by using a calculator, it's easy to show that the answer is 1,591. On the other hand, if I say, what two numbers can I multiply other than having one of them be the number 1? I have to be careful how I word that. If I say to a student, give me two numbers which when I multiply them together gives me 1,591, all they have to say is 1,591 times 1. So we usually say 2 factors greater than 1. Well, you see, it's much easier to take the two numbers and multiply them together than to try to unscramble the product and figure out what the two numbers were. So this is kind of what we're going to be working on. And to get into the flow of this, let me just review again. And the thing I want you to really pay attention to is I'm never referring to fractions. Everything we're talking about now is stuff that we should be able to explain to students if they really understand the 4 basic operations of arithmetic. See, the fact that 24 is 4 times 6. See, it's easy to see that 4 times 6 is 24. But if somebody gives you 24, well, it could be 4 times 6. It could be 12 times 2. It could be 3 times 8, but let's suppose we just look at 4 times 6. What that tells us is that 24 is the 4th multiple of 6 and the 6th multiple of 4. In other words, if you're counting by 6s, 24 should be the 4th number you come to, and if you're counting by 4s, it should be the 6th number you come to. That is much easier than having to draw this whole thing out and counting. Let's see where 24 is here. The 1st multiple of 6, 2nd, 3rd, 4th multiple of 6. Where is it over here? We're counting by 4s, what the kids call skip counting. 1 4, 2 4s, 3 4s, 5 4s, 1 4, 2 4, 3 4s, 4 4s, 5 4s, 6 4s, 24. But notice that even though 24 is a common multiple, it's not the least common multiple. See, notice the first number that appears on both lists is 12. Now, as this lecture progresses, I'll show you how we could have found that without having to list all the numbers. But for the time being, let me just refresh what we've done. The product of two whole numbers is always a common multiple of both numbers, but not always the least common multiple. Let me give you a word problem based on that. And it's one that I don't know where the data comes from. I saw it in a problem myself, and I just thought it fit here rather nicely. I really can't verify that hot dogs usually come in packages of 8, especially since the brand I buy, they come in packages of 10. And I can't verify that hot dog buns usually come in packages of 10 because the ones I buy usually come in packages of 12. But that's the nice part about math. You see, what you really should be saying is if. See, now if I put the word if in here, I don't even have to use usually. I'm just giving you a hypothetical situation. If hot dogs come in packages of 8, while hot dog buns, I'll cross these out now, come in packages of 10, how many packages of each should I buy to make sure I have exactly the same number of hot dogs as I have buns? Again, not a really good real world problem, because in the real world we say, who cares? If I have a few hot dogs left over, I'll have them tomorrow. If there are a few buns left over, I'll stuff them with tuna fish salad. This is how we get around math sometimes. If you don't want to follow the recipe exactly, if you have only, say, 3 people coming and the recipe serves 6, rather than do fractional parts, you make the recipe for 6 and just give everybody a bigger portion, or you save some for the next day. But what happens is there are real-life situations where the math has to be exact, and we'll talk more about that as the course progresses. Well, the long way of doing this is say, let's see how many hot dogs you get as you buy the packages. See, the 8 is modifying the number of hot dogs, but where it appears modifies the number of packages. See, 8, if you buy 1 package, there's 8 hot dogs, 2 is 16. You skip counting by 8s over here. So the hot dogs, you can either get 8, 16, 24, 32, 40, 48, 56, 64, 72, 80, or 88. Now the buns come in packages of 10. Okay, so the 10 here represents the number of buns, but where it appears tells you how many packages you're buying. You can get 10, 20, 30, 40, 50, 60, 70, 80, 90, or 100. Okay? So how can I tell when I would have the same number of hot dogs and the same number of buns? Whenever the same number appears on both lists. The first number I find that fits on both lists is 40. And what that tells me is buy 5 packages of hot dogs, see, 1, 2, 3, 4, 5, and 4 packages of buns, 1, 2, 3, 4. Very neat, except if we now say, hey, there was a faster way of finding this, just multiply the 8 times the 10 and get 80. See, 80 is what? The 8th number if you come to when you're counting by 10s, and the 10th number you come to when you're counting by 8s. 80 would also work, yeah, but, and that's true, 80 is on both lists, but it's not the least one. And the question comes up, well, who really cares whether it's the least or not? As long as we get a common one, okay? Well, the reason we care comes up in the sense, down the road, we're going to be dealing with fractional parts. You could, for example, have a business partner who reimburses you $10 for every $15 that you spend. You can have another partner who reimburses you $7 for every $24 you spend, and a third partner, say, who reimburses you $3 for every $35 that you spend. So spending a certain amount of money, this is the fractional part they will reimburse you for. And so somehow or other, you're going to be able to have to add these together. And the problem is, you can't just add the 2, the 7, and the 3. Well, I mean, you can, but you get the wrong answer, because the 2 is modifying every $15, the 7 is modifying every $24, and the 3 is modifying every $35. So you have to find a common multiple of these. Well, one way to find a common multiple is to multiply them all together. And I'll share you the grief of having to do that. I did that ahead of time. 15 times 24 times 35 comes out to be 12,600. And already you can begin to sense how long these lists are going to be if you try to do this by listing the multiples. In fact, we can go one step further. If you want to see what multiple of 15 this is a neat way when everything is broken down and you can see the factors. Now, let me use this guy. I'll use this guy. What you do is circle the 15 and see what's left. What's left is 24 times 35. So what do you have to multiply 15 by to get 12,600? 24 times 35, which happens to be 840. This says if you were listing the multiples of 15, you'd have to go out 840 places before you got to 12,600. In a similar way, if you want to see how far you have to go if you're dealing with 24. Cover up the 24, and you see what you have to multiply by is 15 times 35. 15 times 35 is 525. That tells you with 20, if you're listing the multiples of 24, it would be the 525th one you would come to. And in a similar way, covering up the 15 and the 24, we see how many 35s we need. 15 times 24 is 360. So if you're counting by 35s, it would be the 360th number you come to. And can you see how tedious that is and why you might want to find a smaller number that works? Now, to lead into that, this is where I'm going to show you the importance of prime numbers. It's not that difficult. I think if you just pay a little bit of attention, it's kind of exciting. Here I've listed the multiples of 6. It's a very prestigious organization. We call it the 6 Club. 6 belongs, 12 belongs, 18 belongs, 24 belongs, 30 belongs, 36 belongs, 42 belongs, 48 belongs, etc. Number 4 would like to join, but he's not eligible. These are the only numbers that are eligible to belong to this club. Number 9 would also like to join, but he's not in this club. So they arrange a marriage of convenience. 4 and 9 say, let's get married. And married means we'll multiply one another. 4 times 9 is 36, and lo and behold, 36 is on this list. Individually, these guys couldn't make, I shouldn't say guys, these two numbers couldn't make it. But by getting married, meaning by multiplying one by the other, they did get on the list. Now, why did that happen? Well, one way to look at this is that to be divisible by 6, what are the, see, 6 is not a prime number. Doesn't 6 break down into 2 times 3? So any multiple of 6 is a multiple of 2 times 3. In other words, to belong to this list, you have to be divisible by both 2 and 3. Now, why didn't 4 belong? Well, 4 breaks down into 2 times 2. 4 has the right number of 2's. He's got in fact, all he needs is 1 2. He's got 2 of them. He doesn't have the 3. What happened to 9? 9 had the 3, but it didn't have the 2. What happens when they got married? Now they're 2 times 2 times 3 times 3. And now what happens is what? In the marriage, they pick up the 2 from one of the partners and the 3 from the other. And in fact, what that tells me is that not only does 6 belong to this list, but it's also what? 2 times 3, the 6th number on the list. 1, 2, 3, 4, 5, 6. Well, let's continue this story. We'll make this a nice tale to tell the kids. Eventually, a more elite club comes to town, and that's the 5 Club. Okay? And the 5 Club has as its members 5, 10, 15, 20, 25, 30, 35, 40, 45. Again, 4 is not eligible to join. He's not on the list. Okay? 9 is not on the list. So they try the same trick. They get married this time, 36, still not on the list. Now, why did it work here and it didn't work here? And the answer is because here, 5 is a prime number. And that means you can't hide in 5. In other words, the only numbers that divide 5, the only factors of 5 are 1 and 5. You can't make up from one part of 5 and one from another part of 5 without being a multiple of 5 yourself. In other words, the only way you can belong to this list is to already be a multiple of 5. Okay? So what's the beauty of a prime number? If you break something down into prime numbers, you know nothing else can be hidden. So let's go back to the hot dogs and bun problem and see how we could have got 40 just by using what we just observed. 8 is what? It's 2 times 4, and the 4 breaks down to 2 times 2. So in terms of prime factors, 8 is 2 times 2 times 2. So any multiple of 8 has to have at least what in it? 2 times 2 times 2. So in other words, any multiple of 8 works for this guy. Now, what works for this guy? In terms of prime factors, this guy breaks down into 2 times 5. That means, since these can't be broken down any further, to be on the list, the number has to be divisible by both 2 and by 5. Well, we already have 3 2s over here. Do I have to tack any more 2s on here? No. If I have 3 2s, I already have enough to take care of this guy. What's missing? The 5. So I'll multiply by 5. Now do I have a number that's divisible by both 8 and 10? Yeah, because the 2 times 2 times 2 takes care of the 8, and the 5 times 2 takes care of the 10. Now what is that number? 2 times 2 is 4, times 2 is 8, times 5 is 40. And that checks with what we saw before when we showed that if you list the multiples of 8 and you list the multiples of 10, 40 is the first one that appears. And in fact, now we can go one step further and say any common multiple of 8 and 10 has to be a multiple of 40. Nothing smaller than 40 can work. And why is that? Because if I leave out the 5, okay, the number won't be divisible by 8. And if I leave out one of the 2s, the number won't be divisible by 10. If I leave out one of the 2s, what happens? I don't have enough 2s to take care of the 8. If I leave out the 5, I don't have enough 5s to take care of the 10. So 40 is not only a common multiple, nothing smaller works, because if I omit any one of these factors, at least one of the numbers won't be a multiple of it. Let's go back to our 15, 24, and 35 and revisit that one. See, to be a multiple of 15, what does the number have to look like? 15 breaks down into 3 times 5. So to be a multiple of 15, we'll call that number n for number. The number has to look like what? 3 times 5 times something. It has to at least have a 3 times 5 in it. What does it need to be a multiple of 24? Well, 24 breaks down into 2 times 12. 12 breaks down to 2 times 6. 6 breaks down to 2 times 3. So in terms of prime factors, 24 is 3 factors of 2 and a factor of 3. Now, what do we already have here? We already have the factor of 3. We don't have any factors of 2 over here, so I have to put in the 3 factors of 2. See, now this number will be divisible by both 15. See, there's the 3 times 5. It'll also be divisible by 24, because I have the 3 2s and the 3. What do I need for it to be divisible by 35? I need a 5 and a 7. I already have the 5, so the only other factor I need is a 7. So the number I'm looking for has to be 3 times 5 times 2 times 2 times 2 times 7 times whatever, any number you want. 3 times 5 is 15, times 2 is 30, times 2 is 60, times 2 is 120, times 7 is 840. So the smallest common multiple of 15, 24, and 35 is 840. And you might then ask, well, it's the smallest common multiple, where would it appear on the list? Well, what you do is, let's see what multiple of 15 840 is. Cover up the 15, and what's left is what? 2 times 2 times 2, which is 8, times 7 is 56. That says 840 would be the 56th number that would come up if you were listing all the multiples of 15. And where would 24 come up here? You cover up the 3 2s and the 3, the 5 and the 7 are left. It's what? The 35th number you'd come to if you're multiplying by 24, if 24 is the thing you're counting. What multiple is it of 35? 35 is the 5 times the 7. That leaves the 3 times 2 times 2 times 2. That's 24. And what this says is, if you were taking the time to list all these multiples, you would have had the patience and not make a mistake in doing it, and have enough of an eye to catch it, to go all the way out to the 56th number when you're on the 15s line, the 35th number when you're on the 24th line, the 24th number when you're on the 35 multiple line. What's the likelihood that you're going to have the patience to ever go that far? You see? See the beauty of being able to break things down into factors and the like? Well, I think that's enough again for today. So let's leave us again with the practice problem. And I think this can be fun for you and the students if you want. And let's find the least common, the least whole number. And I always emphasize non-zero because the reason is every number is divisible by 0. If you say, what do I have to multiply 12 by to get 0? You say 0. Any number of zeros is still 0. So I will usually emphasize, just to remind you, that when we're talking about the whole numbers, we mean whole numbers starting with 1, which we sometimes call the natural numbers. So what is the least whole number that is divisible by 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10? Pause the video here. See if you can come up with the answer. Whether you can or you can't, come back, resume watching, and listen to my comments, okay? Well, let me start with the answer. The answer happens to be 2,520. So if somebody says, tell me a nice thing about the number 2,520, you can say it's the smallest non-zero whole number that's divisible by 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. You could also have found the common multiple just by multiplying all of these guys together. And that would give you a very nice number, 3,628,800. And in fact, if you take that number and divide it by 2,520, you get 1,440. And that tells you that by multiplying all of these together, you get a number that was 1,440 times bigger than what it had to be. Well, let's see how we get this 2,520. To be divisible by 2, a number has to have the form 2 times something, okay? Whatever it happens to be. Now we want that same number to be divisible by 3. Well, we already have the 2 here, so all we need is a 3. So the smallest whole number that's divisible by both 2 and 3 would be 2 times 3, which is 6. What do we need to make something divisible by 4? 4 breaks down into prime factors into 2 times 2. We already have one of the factors of 2, so we tack on one more. And what answer do we get that way? 2 times 3 times 2, 6 times 2 is 12. Isn't that the number in a dozen? Why is 12 a nice number to have in a dozen? Because it's the smallest whole number that's divisible by 1, 2, 3, 4. Okay? What else is it going to be? Okay? 6, 12. Okay? Now, what do we need to have a number divisible by 5 if we're counting by the multiples of 5? Well, 5 is already a prime number. It doesn't break down any further. So what I'm going to have to do is multiply this number by 5. This part was 12. 12 times 5 is 60. 60 is already divisible by 6. So in other words, what do I know about the number 60, which happens to be the number of seconds in a minute, the number of minutes in an hour? 60 is what? It's the first number greater than 1, the first whole number greater than 1, that's divisible by 1, 2, 3, 4, 5, and 6. The next number would be 7. 7 is a prime number. It's not divisible by any of these guys, so I now have to multiply by 7. What would I need to make this number be divisible by 8? To make it divisible by 8, 8 breaks down to 2 times 2 times 2. I only have 2 factors of 2 here, so I have to tack on one more to make my 3 factors of 2. So this number here, whatever it is now divisible by 1, 2, 3, 4, 5, 6, 7, and 8. What do I need to make it divisible by? 9. 9 breaks down to 3 times 3. I only have 1 3 on my list so far, so I need one more factor of 3. So this would be the smallest number that's divisible by 1, 2, 3, 4, 5, 6, 7, 8, and 9. 10 breaks down into 2 times 5. I already have the 2 and the 5, so the smallest number that would work is whatever this number here happens to be. And I'll spare you we can multiply it out if you want. 6 times 2 is 12, times 5 is 60, times 7 is 420, times 2 is 840, times 3 is 2,520. And by the way, another beautiful thing about breaking numbers down into prime factors is I can tell just by looking what all the other factors of this number are. Suppose a person says it's 2,520 divisible by 14. Well, what does 14 break down into? 2 times 7. I have these both on this list, so is this number divisible by 14? Yes. Is this number divisible by 22? Well, 22 breaks down into 2 times 11. I have the 2, but 11 is a prime factor that's not on here, so 22 won't be on here. Are you beginning to see all the stuff you can do just by understanding breaking down numbers into prime factors? We're going to keep working on this, but again, I think we've done enough for today, so I will see you again next time, and until then, stay well, have lots of fun, work hard.